Gravity is the force in nature by which all objects in the universe attract all other objects in the universe. This universal force is what keeps us on the Earth. Without it, we would fly off into space at hundreds of miles an hour. Gravity dominates the universe on a large scale, being the binding force of planetary systems, galaxies, and galactic clusters. Gravity was the first force in nature to be discovered, a theory which was published in 1687 by Sir Isaac Newton. However, it was first scientifically studied by Galileo Galilee. While gravity is one of 5 fundamental forces of nature, it is unique in a number of ways. Despite its dominance on large scales, gravity is actually the weakest of the 5 forces, being about 1 over 10 to the 36th the strength of electromagnetism, which is why a small magnet can counter the Earth's gravity. It is also the only one of the 5 forces that show no evidence of having a mediating particle, being most successfully explained as a stretching of space-time. While the theory of gravity was published by Sir Isaac Newton, to fully understand the history behind it requires going back before Newton. Though they did not call it gravity, his predecessors laid the groundwork for the Newtonian theory of gravity. These predecessors include Aristotle, Galileo Galilee, and Johannes Kepler. Each provided pieces of the puzzle, but Newton put them together. Aristotle was a Greek philosopher that lived from 384 BC to 322 BC, and he is the earliest recorded person to speculate about physics. Unfortunately, never really tested his philosophy-based physics, yet it was accepted without question based on his authority for about 2,000 years. Aristotle explained gravity by imagining that all bodies move towards their natural place. In his physics, he imagined 4 elements: earth, water, air, and fire. The natural place of earth was the center of the universe, which was considered to be the earth. The natural place of water was seen as a concentric shell around earth. Air's natural place was seen as a concentric shell around the natural place of water, bordering at sea level. And the natural place of fire was seen as a concentric shell around the air. As a result, terrestrial objects would tend to move towards different parts of the universe with a speed based on their composition of the 4 elements. Earth being considered the heaviest element, objects with more earth would fall faster than objects with less earth, and even rise if they were made mainly of air and fire. As a result, Aristotle reasoned heavier objects fall faster than lighter objects, but he never tested it. Aristotle was ultimately proven wrong, but it took 2,000 years simply because no one bothered to test it. Aristotelian physics did, however, serve as a starting point, but ultimately led to the beginnings of science. Galileo Galilei can be considered the father of the science of physics, and in many ways what we today call science. Galileo lived from 1564 to 1642, and he championed both experimentation and mathematics, which are foundational to modern science. For the record, his problems with the Catholic Church resulted mainly from the fact that he was seen as a challenge to the authority of the Roman Catholic Church rather than heliocentrism itself. The historical context of Galileo's persecution by the Roman Catholic Church is often ignored, but it is needed to fully understand the event. His trial by the Roman Catholic Church occurred as the Protestant Reformation was in full swing, having been started by Martin Luther in 1517. It occurred after he attacked Pope Urban VIII in his book Dialogue Concerning the Two Chief World Systems. The Pope saw Galileo as a threat to what was left of his power, and so he was tried and found guilty of heresy by the Inquisition in 1615. While Galileo is most known for his support of heliocentrism, he made the breakthrough that eventually destroyed Aristotelian physics. He did so by doing something that does not seem to have been done in the nearly 2,000 years since Aristotle lived. He put the idea to the test and showed that objects of different weight fall at the same rate. Galileo made this breakthrough by considering that 2 objects of the same weight would fall at the same rate. This would be the case even according to Aristotelian physics. Likewise, 3 objects of the same weight would fall at the same rate. This would also be the case according to Aristotelian physics. Furthermore, the 3 objects of the same rate would fall at the same rate even if 2 were attached. This would be the case as well according to Aristotelian physics. Galileo concluded that this would be identical to 2 objects of different weight falling together. He correctly concluded that objects fall at the same rate regardless of their weight. This meant that Aristotle was wrong and gave him a way to test the 2 views. To test this, Galileo is commonly thought to have dropped 2 cannonballs of different weights from the Leaning Tower of Pisa. Even if Galileo never actually did this experiment, it was done on the moon during the Apollo 15 mission as shown in the following video.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Johannes Kepler lived from 1571 to 1630. His contribution to gravity was the discovery that planets orbit the sun in elliptical rather than circular orbits. This discovery resulted in his laws of planetary motion. Number 1. The orbit of every planet is an ellipse, with the sun at one of the two foci. This describes the relationship between the planet's orbit and the position of the sun. Number 2. A line joining a planet and the sun sweeps out equal areas during equal intervals of time. This showed that the planets moved faster when closer to the sun than when they were further away. Number 3. The square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. This describes the relationship between the size of a planet's orbit and their orbital period. These three laws played a major role in the development of gravity. While Kepler made no apparent effort to find out why planets follow the paths they do, his discovery of these patterns paved the way for future development. Sir Isaac Newton was an English physicist and mathematician who lived 1642 to 1727. He was the one who was actually responsible for the term gravity and the development of the theory of gravity. He didn't provide a mechanism for how gravity worked, but simply described how it worked. His main breakthrough was the realization that the same force that causes objects to fall governs the motion of the planet. The other factors that helped Newton develop his theory of gravity was that he had already developed theories of force and motion. He had also developed the mathematics of calculus, which gave him the mathematical tools to work it out. Now known as the universal law of gravitation, it can be summed up in the simple formula: force equals the gravitational constant times the mass of each of the two bodies divided by the square of the distance between the center of mass of each body. Put into English, this means that the strength of gravity decreases by the square of the distance between the two objects as that distance increases, as shown in this graph. Newton's law of universal gravitation is so accurate that it is still used in calculating spaceflight paths. However, it turns out to be only a very close approximation of gravity. So close that it is accurate in most circumstances, but it is still just an approximation. Albert Einstein was a German-born theoretical physicist who lived 1879 to 1955. His contribution to gravity came in the form of his general theory of relativity. General relativity not only describes how the effects produced by gravity behave, but what actually causes gravity. General relativity shows gravity to be a warping of the fabric of space-time caused by the presence of matter. This image is a two-dimensional visualization of the space-time distortion. It is this warping that is interpreted as gravity. It is the force being applied back on the mass by space-time that results in the observed force between masses. So far, general relativity has passed every test given it. The only real holdouts are gravity waves, but they are extremely weak and difficult to detect. The one thing that general relativity seems to have a problem with is galactic rotation rate, but this suggests either the presence of dark matter or a need for a modification to general relativity. The basic concept of gravity is that it is a force that attracts every particle in the universe to every other particle in the universe. While general relativity shows gravity to be a warping of the fabric of space-time caused by the presence of matter, it does not change the fact that this is the result. While not perfect, Newton's law of universal gravitation is accurate enough for most calculations, only deviating significantly in strong gravity. The Sun has a strong enough gravitational field to show these differences in a small but detectable manner, but it becomes obvious near black holes. The force of gravity between two bodies gets larger as the mass of each body gets larger, but it gets smaller as the two bodies get further apart by the square of the distance. As a result, when an object is close to a larger object, like the Earth, it has a fairly strong gravitational force, but it quickly drops as the object gets further away. This is why, despite the fact that the Sun is much larger than the Earth, that the Earth's gravitational force is stronger than the Sun's near or on the Earth. The result is that as an object falls, it will accelerate. It also means that two objects will accelerate at the same rate as they fall. This is the case even when the two objects have different masses. There is an anomaly in galactic rotation measurements that has led to two theoretical modifications of gravity. Both Newtonian and general relativistic gravity would tend to predict that the orbital velocities of stars, as they get further from the center of the galaxy, should follow line A in this graph, but in reality they follow line B. This anomaly is called the galaxy rotation problem.
The standard model for dealing with this is that there exists a sphere of non-luminous matter around galaxies, referred to as dark matter. However, two new theories have been proposed as alternatives. One is modified Newtonian dynamics, or MOD theory, which is a modification to the way gravity interacts with matter over long distances. The other is called cosmological relativity, which is an extension of the principles of special and general relativity to cosmological scales. Modified Newtonian dynamics was developed specifically to deal with the galactic rotation problem. This makes it as ad hoc a model as dark matter, but without dark matter's simplicity. One other drawback is that it can only be tested by observing things at galactic distance. Dark matter, on the other hand, at least has the potential of being discovered in a lab, and some observations may have already done so. Cosmological relativity was not developed to explain galactic rotation, but does so anyway. This means that unlike MOD theory and dark matter, it is not ad hoc. However, it has the unique distinction of actually predicting the observed acceleration of the expansion of the universe. In conclusion, on the large scale, gravity is the main binding force of the universe. Developing our current understanding of gravity has taken centuries, but it is now fairly well understood, even though there is room for further development. This is particularly the case on the small scale. The main area where development is still needed is in the area of bringing gravity down to quantum levels.